Okay, so welcome back to this session where we're going to hear about 4 nice results in the area of multi-party computation and interactive proofs. So in the first presentation, we will hear about multi-party computation in the setting of a mixed adversary, where we're not considering all corruptions to be passive or all to be active, but where some may be like this and some may be like that. So this model has been considered before, but previous solutions had a pretty bad complexity, while this new work achieves a linear overhead. The work borrows several known techniques like beaver triples, hyperinvertible matrices, planar elimination, and so forth. But all these techniques require new ideas in order to work in this considered mixed adversary setting. Then in the second presentation, that one is also on multi-party computation and on improving efficiency, but now in a standard active security setting, but with a focus on real-world efficiency, considering the actual workings of CPUs, which makes it attractive to consider MPC over integers modulo 2 to the m rather than over finite fields. Now, their protocols are obtained by improving and combining previous techniques, some of which work generically over rings, others were originally designed for the field case and are now made to work here as well by cleverly switching back and forth between sharings over the integers, modulo prime, and modulo power of 2. Theoretical results are complemented with implementations of their protocols and with benchmarking tests, which underline and demonstrate the practical efficiency of their protocols. And then in the third presentation, we're switching gears a bit and move to the topic of interactive proofs, but not in the standard setting with one prover and one verifier, but in the so-called multi-prover setting, where we consider 2 or more provers that are assumed not to talk to each other. Now, in order to enforce this non-talking assumption by relativistic means, so meaning you put the 2 provers sufficiently far apart so they don't have time to communicate, it is important to have low communication complexity, to have really high sort of a clock rate. Now, in this talk, we will see a new relativistic zero-knowledge proof for 3-colorability that requires surprisingly little communication. At the core of the construction is a new kind of commitment scheme, which with so-called implicit unveiling, which is an extremely neat idea. And then finally, in the last presentation, that one is also related to multi-prover interactive proofs, but more from a complexity theoretic angle and in the context of the general question whether structured computational problems are necessary for cryptography. So what they concretely show is that from a black box perspective, hardness in MIP intersect co-MIP is not necessary to realize IO plus one-way functions. Now, this new result strengthens and unifies previous work on the topic. The main hurdle here in this new result is that the verifier for languages in MIP intersect co-MIP is allowed to be randomized, whereas the previous known results were relying on a deterministic verifier. Okay, so that's my short summary of what you can expect in the next few talks. And so now I hand over to the first speaker of this session, which is Marta Mularczyk.
Yes, thank you. So I guess you can see the slides. Yeah, perfect. So this is joint work with Marta and Hirt. We're both from ETH. Since this is the first talk about MPC, I'm going to tell you what multi-party computation is. So we have a bunch of users who have some inputs and they want to evaluate some function of their inputs, but they don't trust each other, so they don't want to reveal anything about their inputs to each other. So this means that ideally they would have this ideal trusted third party who just evaluates a function. But of course, this means that we would have to trust the party, so this we don't want to do. So what the users do instead is to run some, to distribute the trust between many parties who run some sort of distributed protocol. And here the guarantee is that as long as not so many of the parties are corrupted, this is just as good as this ideal trusted third party. Good. So In this work, we consider one particular setting of MPC, where parties evaluate a circuit over a finite field. So here we assume that we do have a field, not a ring. We want to maximize efficiency. So this means that we want to minimize the number of field elements that the parties will communicate per gate. And we want perfect security. So this means against unbounded adversary without error and with guaranteed output delivery, and against a threshold adversary. So there are many corruption types that are considered in the literature, and the standard corruption types are active corruptions, where the adversary fully controls the parties. So this is very strong, but we pay for this in that for perfect security, we can only tolerate up to n-third corruption, so not so many. Then we can have more benign adversaries. For example, passive adversaries don't control the parties, but only see the states. And here we can tolerate more. Now, the downside is that if a single party crashes, these protocols don't give any guarantees. And then we have also fail-stop adversaries, which are kind of not so interesting because they're super weak. They don't see any internal states and just crash parties. And yeah, this is super weak. So all of these settings have kind of advantages and disadvantages. So now I have my my application. I have some setting, and I want to choose a protocol. This is kind of not very flexible because I have to choose one of these three, and maybe none of them is actually suited for my application. So what if I want something in between? For example, I want to trade off a bit of passive corruptions for more fail-stop corruptions, or maybe a bit of passive corruptions, but a few active corruptions because people are usually not actively corrupted. So if you want more flexibility, what you should use perhaps is the mixed setting introduced by Fitzi et al. And it kind of generalizes all of these settings and all of the settings in between. So here a protocol is parameterized by these three thresholds, T8, TP, and TF. It works with fewer than T8 active corruptions, fewer than TP passive, and fewer than TF fail-stop. So you give these parameters to the protocol, and the protocol works. And this is possible if and only if this equation holds. So this is very flexible, but what about communication cost? So as I said, we want to minimize the number of field elements sent, and we want measure complexity in the number of parties n, in the circuit size c, so the number of gates, and circuit depth, so this is multiplicative depth of the circuit. So for the pure settings, we have super efficient protocols which are linear in the number of in the circuit size and the number of parties. Yeah, so for the passive setting, we have the protocol by Damgaard and Nielsen. For the active setting, we have last year, actually, we have the first linear protocol. The first one had also this quadratic term. But for the mixed setting, what we are left with is this first feasibility result, which builds on BGW and is as inefficient as BGW. So for some reasonable parameters, this means that parties have to communicate like terabytes of data. And this is just impossible to implement. We can't even hope for this. So this is what we wanted to fix in this work. And so we have a protocol which is linear in the number of parties and in the circuit size, but we also have this quadratic term as the BH08 protocol. And I want to stress that even for very bad circuits, we have quadratic complexity, which is orders of magnitude better. So this is possible to implement somehow. We can hope for this. Yeah, so this is our result. Now, just one slide with our techniques. So we use these amazing techniques for the active setting. Unfortunately, in the mixed setting, they sort of break. So the problem is that with so many fail-stop corruptions, if you want to adjust the parameters of these protocols to preserve correctness, you destroy efficiency. And the problem is that roughly all of these techniques somehow distribute work among correct parties. So in the active setting, there are many correct parties, and one can somehow distribute the work. In the mixed setting, it might be that all parties crash, there is no one to distribute work among, and so we lose efficiency. So our solution is to kind of slightly modify maybe the active protocol, and at various points we'll execute this heartbeat, which which is super simple. We just check whether a party crashed by this party sending some value to all parties, and then we run consensus. The downside of this is that consensus costs a lot. We want linear complexity, so we only run it every now and then, and we make sure that privacy is preserved even with crashes. So we can repeat the protocol without the crashed parties. So that's the overview of our technique. And to summarize, we have the flexible protocol for the mixed setting. It's as efficient as active protocols, and it's quite simple, which I think is an advantage, not a disadvantage. Yeah, so thank you.
Thank you.
Should I stop sharing? Or?
So there don't seem to be any urgent questions, so I suggest that we move on to the second presentation, which is going to use our brain, and I think it's given by Mark.
Yes.
So please go ahead, Mark.
Okay, let me just put this on full screen. Yes. Okay, so this paper is called Use Your Brain Arithmetic 3PC for Any Modulus with Active Security. And this is joint work with Hendrik, Eerikson, Marcel, Keller, Claudio, Orlandi, Pille, Pullonen, Joonas, Puura, and me. And as in the previous paper, the setting here is secure computation. So in this paper, we focus on 3 parties. So we have 3-party secure computation where the parties have an input and want to compute some function. And the first 2 adversaries we know from the previous talks. We have passive adversaries that follow the protocol but would like to learn more information. We have active adversaries that misbehave in an arbitrary manner. And the third class of adversaries that one can consider are so-called passive protocols that one can consider are so-called passively secure protocols with weak privacy, where the protocol is passively secure. And in addition, if an adversary misbehaves, then in such a multi-round protocol, the privacy of the honest party's inputs is preserved up to the last round of the protocol. So there are no guarantees on correctness, and there's no guarantee on the privacy of the honest party's inputs after the last round, but up to the last round, the inputs are hidden. Okay. One common flavor of MPC that one can consider is the so-called preprocessing model, where one would like to split kind of the overall runtime of the MPC into 2 phases. So in the offline phase, one would like to generate some correlated randomness, which is independent of the actual inputs and mostly independent of the function that one would like to compute. And then in the online phase, using this correlated randomness and inputs, one would like to execute a very fast information theoretic protocol to compute the desired function. And the idea here is that usually the offline phase is a bit slower, but in exchange, the online phase is a bit faster. So in this paper, we focus on computations over rings. And like to motivate this a little bit is that, so we have like several models of computation that we can consider. And we can consider Boolean circuits for like SHA or IS or computations like this. But if we want to compute something arithmetic in nature, like in our products, like a neural network evaluation or something, then Boolean circuits are not really the right model to represent the computation. So what we usually do is we go to arithmetic circuits over fields. And we go to fields because they provide some very nice structure, which we can use to achieve active security. So we can like use tools like information theoretic max to take a passively secure protocol and lift it to active security. The downside, unfortunately, is that if we look at like a regular computer and like what we usually do in like programming languages, so like something without cryptography, then actually we would like to do computations over 32-bit integers, 64-bit integers. And this is, on the one hand, it's more natural to what we actually want to do in reality. And also because these native data types are faster, we can also hope for like better efficiency if we actually like use those data types rather than some kind of like big integers or like big field elements. So that's why kind of we try here to focus on arithmetic circuits over rings, which are closer to the real world, but kind of introduce new challenges for achieving active security. So what we do in this work is we, as I said, we focus on 3-party computation with 1 active corruption. We construct a compiler that takes any passively secure protocol and constructs any passively secure protocol with weak privacy and constructs a protocol with active security. And then using this compiler in combination with other custom protocols, we kind of construct overall efficient 3-party computation protocols. And to see whether like they are actually efficient, we also implemented them to see what the performance results are. And the whole starting point of this work was really a paper that we had in 2018 at Crypto, where we had a compiler that takes passively secure protocols and transforms them into actively secure protocols. And because the compiler was quite simple, we had the intuition that maybe if we use this compiler, we can actually get practically efficient protocols. So our starting point is this compiler. So just quickly recall it, we have 3 parties and they would like to compute some function and assume they have access to some passively secure protocol. So if a malicious adversary sends a bad message, then potentially the output of the computation will be correct. So now we would like to use this passively secure protocol to generically construct an actively secure protocol from this. And the idea in that paper was that, okay, we introduce a layer of indirection. So the real parties will imagine some virtual parties, and the virtual parties will compute the function on their behalf. And the real parties now will simulate the virtual parties in some appropriate manner. So in this case, we have the virtual parties in the clouds, and the real parties next to each other will always simulate that virtual party. So for every virtual party, we have 2 real parties simulating it. On the other hand, for every real party simulates 2 virtual parties, okay? And the idea is that now the virtual parties will execute the protocol, and then the real parties get the output. And the way this was done is that assume magically that the real parties for each of the virtual parties agreed on a random tape and agreed on some input for that virtual party. So now whenever one virtual party sends a message to another virtual party, all of the real parties that simulate the sender can send one message to each party that simulates the receiver. And now because we consider only one act of corruption, we know that if the adversary misbehaves, then the other party is honest and it will send a message that is inconsistent. So in here from Alice's view, if the messages that she received are consistent, everything is good. If the messages are inconsistent, then she can abort because she knows that the adversary tried to like misbehave in the protocol. So this is kind of like the very high level of the protocol. And when we look at the efficiency, basically for every single virtual message, we need to send 3 real messages. And why do we need to do this? Because it's a passively secure protocol. We need to ensure that Alice never answers to a maliciously formed message. So Alice always needs to immediately check the correctness. And kind of the idea here is that if we have a slightly stronger assumption on the passively secure protocol, then we can delay this check. So what we basically do is we assume that we have a protocol with weak privacy. And now again, kind of the real parties magically agree on inputs and random tapes. And then in the second phase, the protocols execute, the parties execute the protocol. And then in the third phase, they basically do one check that all the messages that were sent were correct, rather than doing a check at every sent message. So now if we have one virtual party sending a message to another virtual party, then rather than both of the senders sending the message, we will have one party acting on behalf of that virtual party, whereas the other one for the moment does nothing. So one of the real parties simulating the sender sends the message to all of the receiving real parties. And at this point, Alice cannot check whether she received the correct message or not, but because the protocol has weak privacy, she will simply continue under the assumption that this was actually the correct message. And then in the last round, the second real party that simulates the sender will basically send a digest of all of those messages, which is like a compressed version of all the messages that that sender was supposed to send. And using this information, Alice can then check whether she received all of the correct messages in the previous protocol execution, and can then check whether everything was okay. And kind of like even for 3 parties, we see that now instead of sending 3 messages, we only send 2 messages per virtual message that we would like to send. So the protocol that we compile is basically Beaver's arithmetic circuit evaluation because it's passively secure, it computes over rings. The only thing that we need in addition here is that it also requires some correlated randomness that we need to generate to be able to use that protocol. So kind of the overall approach that we have is that we have custom-made preprocessing protocols for generating this correlated randomness. And then we use the passively secure protocol of Beaver in combination with our compiler to get the online phase to get our overall protocol. And we implemented this stuff and checked how fast it is. So basically we have 3 parties on 3 different continents, and we did computations over 64-bit integers. The implementations are in MP speeds and ShareMind, and we could get over 10 to the 5 multiplications per second. And if we had the parties being on the same continent, then we could get around 10 to the 6 multiplications on per second. Yeah, and basically I skipped a lot of stuff. So there's also a protocol without preprocessing. There are details of the preprocessing protocols and implementation and details. You can find all of those things in the paper. So thank you very much for your attention.
Thank you, Mark. I got sort of one question, but I suggest we'll do the Q&A at the end of the session. So hang around, please, and then I'd like to give the word to Claude for the third presentation.
So good morning, everyone. I'm going to be speaking about practical relativistic zero-knowledge proofs for NP, in particular three-colorability. And I'll say a few words about its entanglement sound version where the provers can be entangled. So this is joint work with Arnaud Massenet, Louis Alvai, Luca Stinchcomb, and Nanyang. Now, most of this talk is going to be about three-colorability. So this is a very small three-colorable graph. This is going to be my example throughout the talk. Now, in practice, we would use much bigger graph, actually much bigger than this one. But for simplicity, this is what we'll stick to for the whole talk. Now, three-coloring of a graph means that it's possible to assign colors to each node, one out of three colors in this case, and so that any two nodes that are attached by an edge must be of different colors. Now, this problem is known to be NP-complete, and we know that in the traditional standard proof, a prover could convince a verifier that a graph is three-colorable just by providing the three coloring. Now, of course, if we do that, this wouldn't be zero knowledge because the verifier would be able to run away with the witness of three coloring and show it to everybody. So in order to avoid that, we would like to get zero knowledge. And in particular, we're going to go the multi-prover way, because the multi-prover way offers the possibility of proving zero knowledge in a perfect or statistical zero knowledge way. And no computational assumption needs to be used. Now, this model has several provers, so this talk will have 2 or 3 provers, and they're allowed to share randomness and agree on a strategy, and they try to convince a verifier, and they want to prove that a certain string W, in our case, a graph is three-colorable, and such languages as three-coloring are in MIP. Now, we require that whenever a string W is indeed in the language, the acceptance probability of the verifier be close to 1. Different notions here, 2/3 is fine. With repetition, we can get as close as we want. This is soundness. And we want completeness, that whenever the string is not in the language, then the acceptance probability should be quite small, whatever the provers do. So even dishonest provers cannot get the verifier to accept. Now, this model has an assumption that during the run of the protocol, the provers cannot communicate. Now, this turns out to be a rather subtle business, but this would be for another talk. Let me just emphasize that it's been suggested by Killian as early as 1990 and then put forward considerably by Adrian Kent that one way of implementing this is by having distance between the provers. Now, enforcing distance between the provers is difficult because you never really can tell where people are, but enforcing distance between verifiers is perfectly feasible. So instead of one verifier, we're going to have 2 verifiers, and they're going to stay away from each other, and they can monitor that. And based on this and the response time of the provers, they can actually assess that the provers are unable to communicate due to the limit of the speed of light. Now, in this model, it is possible to achieve perfect zero knowledge or statistical zero knowledge. However, those versions that we have are not very practical. So one approach is to combine the traditional protocol of Goldreich, Mikhaili, Wigderson to do three-colorability by committing to every color and then getting the verifier to select an edge to be unveiled, and combine that with the multi-prover methodology. That would give a protocol which is sound. However, is it sound against entanglement? Well, when I first looked at this, I didn't know. And I'll tell you later that it can be made entangled sound, but it will not resolve the main issue, is whether it's practical. Now, as I will show you, I don't think this is very practical. And the main reason is because you have to commit to every node. Now, another approach was taken by Chailloux-Leverrier in 2017, and they proved that Blum's Hamiltonian path zero knowledge proof can be made entanglement sound. But unfortunately, it is still not practical. It's actually even less practical than the first approach. Now, why is that? Well, this is a space-time diagram. And on the left, you have a verifier giving information to the first prover so that he can commit. And then the prover sends information back to the verifier to actually commit. Now, on the right, the other verifier is going to request to unveil according to the protocol, and then the prover will unveil. Now, it turns out that in order to get relativity to kick in, we have to make sure that these events are synchronized properly, and this is what the dashed diagonal lines show. And as a matter of fact, okay, I have a small glitch with my slides here, but the Chailloux-Leverrier version of the protocol will have that the distance between the two sets of provers verifier has to go quadratically with the number of vertices, whereas this other approach that's sort of very natural would grow linearly. Now that means that in practice, if you use pretty big commitments and if you use, if you want to implement safety via distance, you have to get your prover verifiers very far from each other. For practical sizes, that would be at least hundreds of kilometers. Now, on the contrary, our approach will use only a logarithmic amount of communication in each round. And by doing so, we can actually implement this. Now, our starting point is, again, this protocol of Goldreich, Michael, Wigderson. We can make it entangled sound by using a powerful theorem, which says that if we add a third prover verifier pair, it will naturally become entangled sound. And this is a powerful theorem of Kempe, Kobayashi, Matsumoto, Toner, and Vidic. And it basically says that if we add a third prover who's making one of the first two, we're going to get entanglement soundness for free. Now, not quite for free, because the soundness error will increase polynomially. Now, our idea is that instead of committing to the whole graph, we're just going to ask one prover to commit to one edge and the other prover to commit to potentially another edge or the same edge. Now, what kind of commitments do we use? We use commitments that are the traditional ones, essentially, but with a small twist. We get one prover to tell a randomness string to the verifier, sorry, a verifier that tells the prover a randomness string that yields a commitment, and then the other one unveils. Now, that's the traditional way of using commitments. Now, the trick of our paper is that we realize that if we get both of them to commit, you can actually get them to unveil obliviously. So if you give them, if you ask them both to commit to a value, and then you give them different randomness, then you can actually establish the colors. But if you don't give them different randomness and give them the same randomness, you will get them to, sorry, I'm completely out of time. So the point is that if you ask different edges with an intersecting node, the bottom one in this example, you can ask one prover to commit to this edge and the other prover to commit to that edge, so sorry, to that edge. And if you ask that with the same randomness, you can corroborate that they give you the same commitments when asked the same node with same randomness. However, if you give them exactly the same edge, but with different randomness, you can actually see the colors. So our protocol is extremely simple. Each prover is going to be asked one edge with two randomness, which are just bits, and they answer back a commitment, which is actually just a trip. And if they're asked the same edge, you can check the color of the two endpoints. And if you give them potentially different edges, but with common nodes, you can check their consistency. Now, if you alternate consistency test, which we call well-definition test, and edge verification test, then we can get a soundness error, which is actually pretty bad. But if we repeat sufficiently many times linearly in the number of edges, we're going to get an exponentially small error probability. Now, let me just skip my argument of soundness. Now, as for simulation, the two provers can be asked arbitrary edges. And we can see that in the case where they're asked arbitrary edges, you can see either no colors at all, one color or two colors, and therefore this will remain zero knowledge. Now for entanglement soundness, we apply the same theorem that I mentioned before. And so the protocol for the entangled case has three provers doing exactly the same kind of work. And in this case, we still get an entangled error, which is quite small, but we have to repeat a fourth power to get exponentially small probability. The zero knowledge simulation still works with three provers, and this is the bare maximum. You cannot go further. Now, let me conclude by saying that an implementation of this is actually being implemented with my colleagues. We had a run about a week ago at about 400 meters, and we're able to get this with reasonable sizes of graphs and decent security parameters. Open questions will come at a later time. Thank you for your attention, and sorry for running out of time so badly.
Thank you, Claude. Thanks. Yeah, also here, let's do the Q&A at the end. So after the next and last talk of this session. So I would like Ido to come on stage.
Okay. Thank you, Serge, for the introduction. This is a joint work with my advisor, Gil Segev. So a starting point for our work is the striking difference between public key primitives and private key primitives, where for private key primitives, we have many candidates, and oftentimes their security is based on the hardness of problems with not much structure, and as a result, current attacks are believed to be nearly the best. However, with public key primitives, we have only a few candidates. Their security is based on the hardness of problems with a strong structure, and we have much less confidence that our attacks are the best, and they are endangered by algorithmic advances, either with a classical or quantum computer. So we ask whether structure is necessary for public key cryptography. So to move on with the discussion, we need to define more carefully what structure is in our context, or when is a computational problem considered structured. And there's no clear-cut answer for this question. However, a popular choice is to say that since one-way functions already imply the existence of hard language in NP, a problem is structured if it is contained in a complexity class not believed to contain NP, such as NP interseco NP and statistical zero knowledge. And the intuition is that we can show that the language belongs to this class by exploiting its structure. And here you can see several hardness assumptions and primitives that belong to these classes. So restating our question, does public key cryptography imply the hardness of a language in such a class? So already in '88, Rudy showed that one-way functions do not imply the existence of a hard problem in NP intersect NP in a black box way. And more recently, Bitansky, Degwaker, and Vaikuntanathan showed that even injective one-way functions, together with indistinguishability obfuscation, or IO for short, does not imply such hard problems in a black box way. And they also showed that they do not imply hard problems in SDK in a black box way. These primitives do imply public key encryption, oblivious transfer, and functional encryption in a black box way. So a consequence of that is that all the primitives on the left-hand side does not imply the existence of a hard problem in NP intersect NP or in a SDK. Now, in our work, we show that these primitives do not imply the existence of a hard problem in AM intersect OAM. And we note that AM intersect OAM contains both NP intersect NP and SDK. So in some sense, we generalize the two results of BDV. However, the result of BDV for SDK applies also for promise problems, while our result applies only for languages. And even more generally, we showed that injective one-way functions together with IO do not imply the existence of hard problems in MIP intersect MIP, where MIP is the class of languages with multi-prover interactive proof. However, this seems a bit too much because NP is contained in MIP intersect MIP, and already one-way functions imply hardness in NP. So this seems like a contradiction. So in the pre-recorded version of this talk, I discussed this in depth. However, a short answer is that if we have a black box construction in some class, it doesn't necessarily imply that we have a black box construction in a class contained in it. And moreover, the same class can have inequivalent definitions of a black box construction. However, to fully understand the meaning of our result, I highly recommend listening to the pre-recorded talk. Okay, so here's a more formal statement of our result, which I don't expect you to fully understand because I didn't define everything. But we showed that there is no fully black box construction of MIP protocols for a worst case hard language and its complement from an injective one-way function F and an indistinguishability obfuscator for F-aided circuits. It's important to note that both the results of BDV and ours are independent. The corollary to public key encryption, oblivious transfer, and functional encryption is independent of whether IO or not exists. So a takeaway message is that public key cryptography does not seem to inherently require even little structure. So we should not lose hope in basing public key cryptography on unstructured problems. So that's it, and thank you for listening.
Thank you. So then we move to the Q&A part. First question I have for Mark. So it's a question by Amit Agarwal, and well, he's asking, if there's anything structurally special about three-party computations. I guess concretely, why is your result about three-party computation? Can you extend it, generalize it to two-party computation or multi-party computation?
So if we are in a two-party computation setting with one corruption, then we cannot hope for information theoretic security. So this would require us to introduce some computational assumptions, whereas our protocol is information theoretically secure. Regarding more than three parties, the modified compiler works for more parties, like for any number of parties, albeit with like a small active corruption threshold. But the protocols that we tailored for like all the building blocks that we need around the compiler, they are specifically for three-party computation. And there is no direct way that I would see right now to extend them efficiently to more than three parties, because they kind of rely on replicated secret sharing, which usually doesn't scale that well if you have more parties.
Okay. Another question, well, that I have, as far as I understand, right, a dishonest party can make your protocol abort, and do parties then realize, I mean, who was the cheating party?
We didn't check whether we have identified. 1 second. We didn't check. So for like we proved everything with regular abort. We didn't look into identifiable abort in this setting. I would need to think about it carefully. Presumably the answer is no. We only have abort for the moment.
Yeah. I mean, that would sort of be my guess, right? Because there's some consistency check, and if that doesn't work out, then you know something went wrong and you're bored. But seems that you would have to some additional thing to figure out sort of why there is this inconsistency.
So we definitely don't have identifiable abort, because if you receive one correct and one incorrect message, I mean, even in the kind of for identifiable and not identifiable abort, one can look at the old compiler, and there basically I receive two messages. One from the adversary, one from the honest party. I cannot tell which of those two is incorrect. So basically, if you would want to have identifiable abort, one simple way to get it is that, like, if you have more than three parties, that you have an honest majority in every set of, for every virtual party, you have a set of real parties that simulate it. If the set contains an honest majority, then you get identifiable abort. That's like the simplest way to get it. For three parties, we didn't look into it more concretely.
Okay, yeah. Thanks, makes sense. I see that Adam has a couple of questions for Claude. Do you want to ask them directly, Adam?
Sure. So one question for Claude. Let's see, just about the model more generally. So you distinguish between like non-communicating provers and entanglement sound provers, but then in your slides, you sort of mentioned like local variables provers, I think. Right. So my understanding is there are like three nested models. There's sort of, classical correlations, entanglement, and then no signaling.
So if you allow me to take the
you can share your screen if you want. Yeah, sure.
Okay, so I guess I'm no longer in share screen mode. Let me.
But just quickly, like, do your
okay. So basically, the assumption that signaling is impossible only implies that whatever requires signaling cannot be done. Now, there's a very broad world of what can be done without signaling, and the original picture that local is what is the opposite of signaling is not sufficient. We realize that quantum allows more than local, and that this is still not signaling, but there's a whole world between quantum and signaling that we call the no signaling world, which is potentially possible, but where we have no physical evidence that we can actually implement these things in our world. So this is theoretically possible. It's stronger than quantum, less than signaling, and it's a broad open question whether our physical world allowed for any of this. Now, for good paranoid cryptographers, our ultimate goal is to show security even against no signaling, because if the assumption is that you cannot communicate, then you mean that you're given any no signaling possibility, unless you can prove that those are impossible physically. And therefore, and this is sort of one of the open problems that I didn't get to mention, proving a similar result for no signaling is the ultimate goal, because right now we can prove soundness against entangled prover. We can actually prove it's not sound against general no signaling provers, this protocol that we have. And therefore, if it turns out our world is more than quantum and that it allows for some of these no signaling possibilities, then we lose the soundness completely. So this is one of the main, and the fact is there are currently absolutely no zero knowledge proofs except for statistical zero knowledge of the standard kind. Anything like NP or more is not done in zero knowledge in the no signaling world at all. I see you have eyebrows moving, but this is it, right? There's no zero knowledge at all in the no signaling world. There are many papers about interactive proofs, but there's no zero knowledge.
That's cool. I have another question, but I want to give other, I don't want to monopolize the time. So I want to let, if there are other questions, I'm happy to wait.
Well, I mean, I have another question to Claude. So your protocol with security against entangled provers requires 3 provers, right?
Currently, I mean, the proof techniques that we're using uses that. However, it doesn't mean that the 2-prover protocol is not sound against entanglement. We just have no idea of the bound if we keep it with 2 provers. It's not that we have a way to break it, but we don't know how to prove a tight soundness bound in that case.
Okay,
so
but potentially sort of the 2-prover version that you have could also be secure in that.
Absolutely, and within the same number of rounds. I mean, it's possible that the protocol, just as we now implement it, is sufficient for entanglement. We just don't have a proof of it.
Yeah, because indeed, I mean, these proofs usually are quite hairy, and sort of your way out is to use this big hammer of these people that you mentioned.
Well, that's basically because I'm good at protocols, but not so good at quantum.
Yeah, sure. No, we're doing good in time. So Adam, I mean, please go ahead and ask your other question as well.
Sure, Claude. This is also a question for Claude. Can you tell us more about the model of sort of the time, like how you're measuring time complexity? So you mentioned that there's sort of this connection between how quickly each prover can interact with its or each verifier can interact with its prover, and the required separation between the verifiers and implicitly the provers.
Yeah, so
and I didn't understand, like, is that based on total communication, or like?
Typically, in the protocols, the older protocols that I mentioned, the provers have to commit to a huge object before they can find out which part they're going to unveil. And so the constraint is that you have to separate the 2 pairs of prover verifiers enough that one prover will be able to commit the whole object to its verifier in such a way that the other prover doesn't find out okay, so the verifier is giving some randomness to the prover to do the commitment, and so the other prover shouldn't find out about that. So the point is that in order to get the first one to commit, you have to put the other provers far away, that from the beginning to the end of the commit phase, he cannot learn about how to commit. And of course, correspondingly, how to unveil. Now, this is why it's so important that you commit to very few things. And this is the approach that we took. So instead of committing the whole thing and unveiling a little bit, we end up committing just the necessary thing and combining them so that you can check soundness, but without having to communicate a lot.
I see. And is there like a lower bound? So you mentioned you get that sort of per round communication down per like unit, which is a couple of messages. There's like 3 or 4 messages. You get that communication down to logarithmic in the instance size, right?
That's right.
Is that is there can you do better than that? Is it conceivable that one could get constant, or is there like a lower bound that says you can't do better than that?
I mean, the bottom line is I suspect you cannot do much better, but I have not even attempted working out a proof of that. But if you want to be able to talk about an object which grows as the size of whatever instance you're dealing with, somehow they have to communicate something about it. And constant seems impossible, but something that grows slower than log might be possible.
I see. Thanks.
Okay, so I have a couple of questions for Marta. Is Marta still around?
Yes, yeah. Sure.
Good. So one question, so if I understand correctly, right, sort of you consider sort of case where you, well, or for every choice of these parameters, TA, TP, TF, that satisfy the inequality, you get a protocol with this complexity that is sort of robust against these sort of given thresholds. Now, what would be really cool, right, would be sort of a universal protocol that works as long as these thresholds satisfy the inequality, but you don't have to fix them in advance. Is that even sort of conceivable?
Well, it's conceivable in general. So we have some computational protocols that are kind of, it's called dynamic thresholds, I think, that have active and passive corruptions. But I don't know of any perfectly secure protocol or even unconditionally secure protocol that does it. It's a very natural question, I think, but I don't know.
Yeah. And sort of the other,
it would be really cool.
Yeah, I agree. I mean, the other question, yeah, so you mentioned, right, in this work, you considered perfect security, or you ask for perfect security. Now, the next level would, of course, be to ask for statistical security, which sort of would sort of potentially allow you to sort of to weaken sort of the restriction on these thresholds.
Yeah.
Parameters. Did you look into that?
We don't have a protocol of so the weakening would be 2TA plus 2TP plus TF smaller n. That's the optimal equation for unconditional security. We don't have a linear protocol for that. I believe that by modifying some active protocols, you can get there for unconditional.
It's possible, but in this setting, protocols usually are sort of more complicated. I mean, particularly if you want to have them efficient.
Yeah. So yeah, I actually don't know of any linear protocol for unconditional. Probably there is one. I just can't cite it right now. I mean, we didn't do everything, right? There are, of course, many open questions that one can ask. So you pointed to obvious ones, right? It's kind of,
yeah. Of course, I mean, you can sort of ask similar questions. I mean, so consider this mixed adversary model in all the different versions, all the different settings where you can do multi-party computation, like non-synchronous model is also something that has been considered.
Yes, with different assumptions, broadcast assumption, I don't know, an incomplete network.
Yeah. Okay, thank you. Are there any other questions from the panel or the participants, or from one speaker to another speaker?
I had a question for Ida. So I didn't, you mentioned a little bit how you resolve this contradiction about how you can show separation from MIP intersect co-MIP even though it contains NP. I guess I didn't understand your short explanation. Could you maybe say a little more, or try to just explain it again?
Sure. So the reason we have this unintuitive phenomena is because the proof of MIP of IP equals P space, and MIP equals NX. They are both non-relativizing, right? So even though one-way functions imply the existence of an NP verifier in a black box way, we cannot take this NP verifier and turn it into an MIP protocol for the complement of the language. So I think our result, like here in high classes where we have such a non-relativizing, non-black box techniques, our results seem weird, but for AM interseco AM, where we don't have such results, we can understand it as more like simply, right?
Okay, great. Thank you. Then I suggest we all thank the four speakers for their very nice presentations. And yeah, that's it for this session. And I guess we're going to continue in 15 minutes, 20 minutes with the